Hi, everyone. Thanks for coming. Yeah, as Matteo said, the title of my talk is TimeCrunch, Interpretable Dynamic Graph Summarization. This is joint work with Danai Koutra from University of Michigan, Tianmin Zhou, and Christos Faloutsos from Carnegie Mellon, and Brian Gallagher from Lawrence Livermore National Lab. Okay, so what exactly is dynamic graph summarization? So the problem we focus on here is given a series of n graph snapshots. These could be static graphs taken at intervals of days, weeks, months, etc. We hope to, we hope to find a concise summary of recurrent, possibly overlapping subgraphs in a scalable and parameter-free way. So, in this example, you can see that across these graphs we may have found interesting graph theoretic structures like bipartite cores or cliques or stars that may be present or non-present at different time steps. So what does this actually look like in real graphs? So we can do all sorts of cool things with this, particularly in community anomaly detection focuses. For example, so actually in all of these figures, ignore the red and blue. This is just for visual distinction. The gray slices represent time steps. And for example, on the far left figure, you notice a near click in a Yahoo instant messaging network of 40 users, a star in a phone call network corresponding perhaps to a boss calling employees, arranged near click, which happens over about 7 years, in a co-authorship network in which authors collaborate. I'll expand more on these later. So motivation. Everybody knows graphs are big. They're hard to understand. There's a number of tools that exist for interpreting static graphs, like clustering, modularity tools, partitioning tools like spectral partitioning, multi-level partitioning like METIS, information theoretic partitioning. And there are a number of visualization tools also for rendering large static graphs on your personal computers. But what about dynamic graphs? In fact, not many tools exist for this, despite the fact that dynamic graphs are pretty much ubiquitous in today's world. So here are a couple of examples. DBLP co-authorship, in which authors collaborate over years. The Twitter social network, in which authors interact, follow each other, etc. Or phone call networks like, for example, Verizon or any other phone call network in which users call each other. So why summarization? Why summarization? Why is this an important problem? So one of the main reasons is for attention routing. For example, if you look at this graph, it's a mess. You probably couldn't tell anything from it. So this is a graph of Wikipedia edits over time. But something like summarization can help a practitioner identify the relevant components of the graph. For example, these two things isolated here in circles are bipartite cores corresponding to edit wars on Wikipedia. It can also help for visualization purposes, rendering large graphs efficiently over time. And more generally, graph understanding the behavioral makeup of graphs over time. Okay, so the main idea of TimeCrunch is essentially we're going to use a dictionary of temporal templates. You can think of these as code words, and we're going to try to use these to compress the temporal graph. Temporal templates can be thought of as a cross product between these static templates, which describe graph connectivity, and temporal signatures, which describe recurrence over time. So for example, we might see something like a periodic star or a flickering bipartite core. We picked these static templates because we know in the past network science research that many of these are indicative of important structures relevant to practitioners. For example, cliques, stars, chains, these are common network topologies. Bipartite cores and cliques are commonly indicative of fraud, and so on. And temporal signatures, because we hypothesize that these are corresponding to interaction patterns that commonly occur between people. And the second idea is we're going to use these templates to try to compress the graph. And we'll do this using minimum description length, which I'll expand on a little bit. But the idea is that whatever compresses the graph best is the best summary of the graph. So these are some details, but to give you some background on MDL, it's essentially a model selection principle, which argues that given a set of models that perhaps could be used to represent your data, the best model is the one which minimizes the encoding cost of the data. So yeah, apologies for the math, but this is essentially saying we want to pick the model which minimizes the cost for encoding the bits of the model and encoding the data, in this case, a temporal graph according to the model. And we can also use MDL to trade off between models. For example, in the top left and bottom left figures, you see that we have a number of points. Say we want to encode the positions of these points. How can we actually do this? So, in the top right model, we might notice that the points have a negative trend. We encode a least squares line using a couple of coefficients, and we encode the errors. Whereas in the bottom right model, we might use a high degree polynomial to encode all the points, which makes no errors, but in fact has high model complexity. Okay, so the formal goal, given a dynamic graph G, a dynamic graph, temporal graph, same thing, we want to use these temporal templates, which I described to you earlier, to find the smallest model M, which minimizes the encoding cost of the graph. We'll encode the temporal graph using this model of templates to describe graph connectivity over time, in addition to some noise or error terms. Okay, so the algorithm. Okay, so we start with an example of just 3 graphs, which could be anything really. You could think of them as 3 days in, say, an instant messaging network, representing user connectivity over time. So the first step, we want to generate some static subgraphs that appear in individual graph snapshots, and we'll label these in some fashion. So, for example, we want to, given a graph, say that this graph is composed of several structures. These structures can be labeled as different types of interesting graph theoretic structures like bipartite core, stars, cliques, and so on. We want to stitch these instances together over time to form temporal instances, and we want to be able to say what kind of recurrence pattern they have. And lastly, we want to compose a graph summary. We want to discard the structures that don't do us any good in compressing the graph, but keep the structures which are interesting to practitioners and compress the graph well. Okay, so first step, we need to actually generate these subgraph structures. This is a hard problem in itself, and there are not a lot of good ways to get them, but one of the good ways is proposed in a paper called VOG by Koutra, who was one of the co-authors in this paper, in SDM 14. And this method essentially operates on static graphs and applies a variety of graph decomposition tools like metas, cross-association, and so on and so forth to extract subgraphs from the overall graph. And it uses MDL to label the subgraphs according to the relevant connectivity patterns. So what VOG would give you is something like this. So say you have a static graph as an input. We might run VOG. We might get some output in terms of some of the common graph theoretic patterns that you might expect to find in the graph and labels for them. Okay, so given that we have these labeled instances from the graphs, how can we actually stitch them together? And when I say stitch, I mean basically group them over time. And moreover, how do we identify the right temporal structure? How do we know that if a clique appears in a number of time steps, how do we know if it's recurring with some kind of periodicity, some frequency, if it's just occurring over a span of time, so on and so forth. So the answer is that for the stitching component, we'll cluster them together using a nice little formulation, which I'll explain in a little bit. And to identify the right temporal structure, we can once again use MDL to identify the temporal signature or structure which encodes the pattern of recurrence best. Okay, so again, we want to stitch together the instances that have the same kind of templates. For example, we want recurrent subgraphs. So there's no sense in matching a clique one day to a chain the next day or a bipartite core, on Thursday. So we'll want to match bipartite cores to bipartite cores, cliques to cliques, chains to chains, so on and so forth. And we want high node overlap between these. There's no sense in joining a clique of 10 nodes today to a different clique of 10 nodes tomorrow. We want recurrence. And so how can we actually do this? So if we naively pairwise compare all of these static instances that we get according to the nodes that comprise them, this is quadratic on the number of instances. It's going to be painful for large graphs, which is our intention. And so the idea is that we can cluster approximately using matrix factorization, which can give us good enough clusterings in linear time. Okay, so the idea here is that we'll create something called a structure node membership matrix. Essentially what this is it's a matrix which contains information about which nodes participate in static instances across time steps. And we'll have one matrix per template type. As I said, we don't want to match different types of templates together, so there's no reason in making our matrix larger than it needs to be. So as an example, consider that we have a clique of myself, Danai, and Christos, and this is the clique of, or this is the structure node membership matrix for full cliques, and we might have 3 instances according to the the red, gray, and the blue full cliques from 3 different time steps. which all encode information about myself, Danai, and Christos participating in these instances over time. Okay, from this matrix, how do we actually get the right clusters? So the idea here is that we're going to extract instance clusters via a process called deflation. Essentially, what we'll do here is we'll repeatedly conduct rank 1 singular value decompositions, and we will prune out clusters from this matrix until the matrix is fully deflated. And because a lot of these structures are going to be overlapping, because we're looking for overlapping subgraphs, we can refine the clustering quality with something like checking for node similarity using Jacquard index or something like this. So I'll illustrate with an example. Okay, so say we start with this graph, or say we start with this matrix of instances and nodes. We run our first rank 1 SVD. We find out that these 4 instances project to the component that we extract. We notice that all of them have very high Jacquard similarity. We don't have any kind of impure clustering here. So let's say we throw this out, and we call that a cluster. Now again, we'll compute an SVD, and we'll notice that in this case, all 5 of the instances will project on our component because they are overlapping. But you might notice that the top 3 instances and the bottom 2 instances are really should probably be clustered separately. But when we refine with Jacquard similarity, we'll see that these bottom 2 instances are not really part of this cluster, and we'll perhaps only throw out the relevant cluster. We'll again do this. Jacquard similarity will be high. We'll prune this out. Our matrix is fully deflated. There's nothing else to do here. So why actually do this deflation process as opposed to doing something like normal singular value decomposition? Well, the advantage here is that deflation is that SVD with deflation is parameter free. We don't need to specify any kind of number of components up front. We don't need to say that we're expecting 50 clusters, 100 clusters, but we kind of just get good enough clusters and as many as we need. We can also do this in linear time. And so that'll make our clustering much simpler than actually going through quadratic pairwise comparisons. Okay, so now that we have these clusters and the time steps in which they appear, we can use MDL to find the best summary for the time series in which they appear. So if we know that let's say this bipartite core appears in time steps 1, 2, and 3, which one of these signatures best describes the recurrence pattern? It could be any of these, but I'll illustrate. So what we'll have is we'll try to encode this time series as a variety of different types of these signatures, or these instances. And whichever one gives us the minimal encoding cost is the one we're actually going to want to use. Obviously, there would be no sense in encoding it as a one-shot structure, because one-shot structures, by definition, only occur one time. And we might formulate the encoding cost for that just by encoding the single time step ID that a structure occurs at. Okay, so for a constant instance, it'll appear throughout time steps. So again, it's a trivial case. This is effectively free because the constant encoding doesn't actually require any bits. There's no real information communicated there. For something more complicated, like a ranged instance, this is an instance that happens, for example, for a week, but stops happening. So they're transient, they're short-lived. For example, if I start calling my friends for 5 days and then I stop calling them, that's an example of a ranged instance. We expect these to have periodicity of roughly 1, as in Monday, Tuesday, Wednesday, Thursday, this type of thing, sequential time steps. And what do we need to encode here? So I'll just illustrate with an example here, and the rest will follow. But we might need to encode the number of time steps using optimal integer codes. We'll need to encode the start and end IDs of our span, and over all the errors that we make. Just by these start and end IDs and some measure of the number of time steps, we can already infer the periodicity and kind of reconstruct the time series of occurrence. But we might make some mistakes. And so we also need to encode these errors. And so for each one of the different types of error magnitudes, we'll encode the actual magnitude of the error. Is it off by 2, off by 3, off by -1, so on. We'll encode the frequency, and we'll actually encode the errors according to optimal codes. I won't go over the details again here, but for a periodic instance, something that occurs at fixed periodicity, for example, every couple of days, every 3 days, every 5 days, so on and so forth, we'll have a similar kind of encoding. For a flickering instance, we kind of have no idea what's happening here. This could be any kind of sporadic occurrence. There's no discernible periodicity, but what we need to encode here is the number of time steps and the IDs at which they occur. This is essentially a lossless model because we don't make any mistakes by virtue of encoding it as exactly as is. Okay, so now that we have a lot of temporal instances, how do we actually compose a summary? So finding the best summary is combinatorial inherently. because we have a lot of overlapping structures, we don't know which ones to keep. And the answer here is that we can actually just use some simple heuristics in practice, and this works quite well. So there are several types of composition strategies we can use. For example, vanilla, which is we encode all the instances naively. We just say everything's a good descriptor of the graph. Top K, we can actually encode just the top K best ones according to some kind of benefit heuristic. Benefit here, it can be construed as the savings that we get by actually encoding the structure as something, as opposed to encoding the structure as nothing, just as noise. And we can actually do something more clever, like a stepwise heuristic, in which we encode in a greedily fashion. We start with the best structures, and every time we encounter a structure that's already been encoded or doesn't contribute to the graph summary, we'll just throw it away. Some applications. So here we find a near click of 40 users with very high density in a Yahoo instant messaging network over 4 weeks. These are spy plots. This could be a botnet or perhaps a large group chat, of 40 users talking to each other. Some people might drop out, but these might also be bots trying to appear normal. Here we have a star of 82 users. Could be boss and employees. Not sure what that is, but we don't have ground truth for these data sets. Here we find a ranged attack on many machines over time. It's a star which forms on 589 targeted machines which are attacked over a span of 2 weeks. DBLP co-authorship, we find about 40 authors which are collaborating very densely together for 7 years, but all of a sudden stop collaborating. This is a phone call data set. This is perhaps one of the most intriguing things we saw. We found a near bipartite core of about 800 callers on December 31st. Don't know what this is, but it could be, for example, handshake calls between well-wishers and receivers on a holiday. Just to summarize, we propose an information theoretic approach for dynamic graph summarization here. Our approach reveals that dynamic graphs have interpretable graph structure. I'll take any questions. These data sets are publicly available, and the code is also available. Feel free to talk to me after the talk as well. Thanks.
All right. Very interesting. Any questions? Yes.
So thanks for the great talk. I had a question about the stability of extracting these subgraphs over time, given small changes in, for example, a near click. Are you able to reliably actually extract at the different time steps the same subgraph?
So the question here was, are we able to reliably extract the same subgraph over time steps? So again, extracting all these interesting subgraphs is a combinatorial problem, and a lot of existing methods like cross-association, metis, and so on and so forth will give us varying results, and the results we get will heavily influence the kinds of structures we find. So we kind of abstract away the problem to existing partitioning methods, but in many cases we find that we are able to extract, if not the exact structure, most of the structure, and that's the reason we only rely on high node similarity as opposed to perfect correspondence over time steps.
Any other questions?
I have one. Sure. Yeah. How was the validation done for the different patterns that you guys got?
Right. So this is a subset of the qualitative validation that we did on about 5 dynamic graphs, and you can read it in more detail about these in the paper. But there was also a number of quantitative experiments on which we evaluated based on how well our summaries were able to compress the graph in terms of number of bits. I've left out the experiments, for the sake of relevance for the talk, but we basically evaluate our summaries by trying to find the number of bits that they use compared to encoding the graph naively, all as error, as opposed to as a model in error.
So the summarization that is got, like, how do you actually say that it's not in terms of the compression that is gotten, but like, is there a ground truth for that? Or
so in some of the sets we have ground truth. For example, in the Enron data set, there is some ground truth that we know in terms of which nodes participate in the Enron social network. But in many of the cases, we don't have ground truth, and we only have this as a tool for practitioners that actually do have ground truth, in which they can for which they can route attention to the relevant problems. So this is kind of just an interesting paper in terms of interesting communities and anomalies that we find. But for practitioners, these could actually mean things like actually finding fraud or finding spam in their data sets. Yeah.
So great talk. Did you try to use this method to predict or forecast what kind of summary statistics you would have next?
Okay, sorry. So the question was, did we use the method to try to predict or forecast structures that we might have in the future? So we actually haven't done that yet. And currently, we only actually operate on recurrent subgraphs. But another point of interest is for graphs which actually evolve, or subgraphs which evolve over time, in which case, in one time step we might have a star, another time step we might have a clique. And this might be able to build more robust models for prediction. But we actually haven't done that yet. That's a good point. Thank you.
So instead of just searching for predetermined like substructures like near cliques, would it be easy to extend this framework or generalize to graphlets of size k, for example? Then you could capture different.
Yeah. So the question was, how easy is it to extend this to other types of subgraphs that might be interesting? And in fact, this is actually one of the advantages of the method. Actually, in terms of the method that I discussed for static summarization for VOG, which will essentially label subgraphs according to some kind of MDL cost. So the nice thing here is that you can formulate any kind of subgraph really that you're looking for, and evaluate it according to your model. And if your model is a good descriptor of the subgraph, then you can really find any subgraph you want. But the problem is that if you have more advanced subgraphs like core periphery structure or jellyfish structure or something like this, then you really need the right kinds of graph decomposition tools to extract these kinds of structures. Many existing tools don't deal with these. They deal with like high modularity or low edge cut partitions or clusters, which will more or less be construed as cliques or near cliques. Yeah.
All right, let's thank the speaker again, and we can put any additional question for the